All right, so now that we've implemented a couple of ways of traversing a tree, spent a lot of time on it, let's talk about which one is better. Which one should you use? And spoiler alert, the answer is that it depends, and there's pros and cons to all of them. And it's really just dependent on your situation, which is always an annoying answer, I know. So let's start by just talking about breadth-first search in general compared to depth-first search in general. So ignoring the order, post-order, pre-order, in-order, put that aside. Breadth versus depth. Which one would you use in a given scenario? Well, I think it depends on the tree. If you have a tree that is fully fleshed out, like this tree, it's as wide as it can be the entire way down. If we're working with a breadth-first search, remember that we have this queue that we're storing all of the nodes we have yet to visit, all of the children. So let's say we're here. We're going to visit this node and then add left and right to a queue, and then go to this node, add left and right. Here, left, right. So our queue grows, and it stores a bunch of pieces of data, a bunch of nodes. So by the time we're down here, or imagine we have something with a height of like 100 levels down, we're going to have to store a ton of data in our queue, just in memory. By the end, that queue will be empty, but I'm talking about space complexity. The time complexity of depth first versus breadth first doesn't matter. They're the same. We're visiting every node one time. So that's irrelevant. But the space that's used up in this scenario could be a lot more if you're talking about breadth first on a wide tree. Versus on depth first, we're not storing all of those nodes across the tree. We only have to keep track of the nodes in a given branch all the way down to the end. And the way that we implemented it earlier in this section was using recursion. So each one of these is a frame in the call stack where we're waiting for something else to happen. So in this sort of tree, where it's a lot wider than it is deep, then depth-first search would use less space. So it's, again, not about time. We're visiting every node once. It's the same amount of work. It's just how much space we take up in the process of doing that work. If we contrast that with this somewhat more depressing binary search tree, if we traverse this entire thing breadth first, the space that we take up in memory is basically nothing. Our queue is never going to have more than one item in it. We start here, we visit this, we add its right node to our queue, and then we move to this, and we pop it off the queue, or we actually shift it. And then we take this, and we add its child to the queue. So we have one thing in memory at any given time, really, in our queue. But if we're traversing it depth first, if this tree is really, really long, then that means a ton of levels that we have to go down and keep every other level above it in memory. So that's something to consider. Most of the time, your trees will look something like, well, I shouldn't say most of the time, but most of my experience is with trees that look something like this, rather than a super, super long one-sided tree, which doesn't make much sense to keep as a tree. Okay, so to summarize that, time complexity is the same. We're visiting every node once. It doesn't matter, if we have 100 nodes, we're going to visit every single one, breadth first and depth first, same amount of time. Space, though, it really depends on the structure of the tree. If it's a really wide tree, breadth first could store or take up a lot more space for that queue. If it's a really deep, long tree, then depth first could end up taking up more space. Okay, the last thing I'd like to do is quickly talk about when or potential use cases for the different variants of depth first search. So pre-order, post-order, and in order. They're all depth first variants. Why would you potentially use one over the other? And there's not really a great answer. I'm going to give you a couple of examples. This is actually a question I put to some of my teacher friends to see what their input was, what they tell their classes. And pretty much the only feedback I got back was, I just teach them and tell them they need to know it because it's good for them. And I don't really have any great examples about when you would use one versus the other. Well, I'm just doing a little bit more than that. I have a couple of examples, but this isn't going to be super comprehensive. But here's one example. When you use in order on a binary search tree, like we have here, if we look at the data we get back, it is in order. We get all the nodes in the tree in their underlying order. So it goes from lowest to highest. So if you want to take an entire large binary search tree where everything to the right is greater than a node, its parent node, everything to the left is less than the parent node, if you use a depth-first traversal in order, you will end up with the set of all the nodes in their order. Depending on what you're doing, that could be useful if you wanted to, grab them in a list or put them in a database or do something with them in that order. It's kind of a stretch, but that is worth knowing that that's a side effect of how this works on a binary search tree. Now, when we talk about pre-order, just to recap how that one works, we visit a node first and then do the left and then the right. And what we end up with, in this case, is a list that looks like 10, 6, 3, 8, 15, 20. And this could be useful if you're trying to clone or duplicate a tree, or you want to store it. You want to like flatten it out so you can store it in a file or in a database or something, and then recreate it from that serialized structure. Basically, you freeze dry it, you suspend it in time, and then when you're ready to rehydrate it, you could go and make this the root and then navigate or iterate through this list, and you make this a child, and you make that a child. And it's given to you in an order where you could reconstruct the tree. Versus if we look at something like this in order, you start off with 3 at the beginning of the list. You don't know what the root of the tree is. Versus here, you immediately know this is the root, this is the left, and so on. So those are just 2 situations where one of those variants might make more sense. But remember, at the end of the day, they're very, very easy to switch between. It's not like you're making some massive decision that you can't undo, right? You just change one line, you move it to the beginning or the end of that function call, and then you have the other order. So really, the bigger concern is breadth first versus depth first. All right, so let's quickly recap trees here. They are a nonlinear data structure. They contain a bunch of nodes. There's a single root, and then usually a bunch of child nodes. Binary trees are a special case where we can have values of any type, but each node can have at most 2 children for a parent. Binary search trees, on the other hand, are a more specific version of a binary tree. So we have trees, and then binary trees, and then binary search trees. And binary search trees have to fulfill a special condition. They are a form of an ordered or a sorted tree. So every node to the left of a parent is less than its value, and every node to the right of a parent is greater. So you can only have a binary search tree with data that is comparable. Pieces of data where you can say this is definitely less than or this is definitely greater than. Okay? And then also, what we just spent a lot of time talking about, we can search or traverse trees using breadth first search and depth first search. And within depth first, there are 3 variants we discussed, 3 orders: in order, post order, and pre-order. Okay, there's a lot about trees. I think I've said this at every section at the very end. I recommend you take a break. Do not try and power through all of this because I'm afraid you're going to lose your mind. Okay.